There's a YouTube video with almost 1 million views called "Open Beams Have a Serious Weakness." And let's be honest, if it were titled "Lateral Torsional Buckling," no one in their sane mind would click on it, except for me and you. Today I'm breaking down the golden rules of steel beam design so you can finally understand what you have been doing for the past 10 years without actually knowing why. By the end of this video, you will realize that what you thought you knew, you actually didn't. And what you didn't know, you really didn't know, if you know what I mean. First things first, a beam can fail in many ways. It could deflect too much, it could vibrate too much, it could fatigue, it could be subject to local buckling, shear, web crushing, or even lateral torsional buckling. But in today's video, we're not gonna talk about deflection, no vibration, no fatigue. Shear, I feel like no one really cares about shear. Shear is like the quiet kid in the corner of the classroom that nobody talks to. But you know what? Shear actually does matter, especially in short, heavily loaded beams or when there's a big concentrated load near the supports. That's when it suddenly decides to cause problems. But we're not gonna talk about shear. If you need to find a beam's shear capacity, just check this table in our engineering second brain and look up for 5EV. And don't forget to assess shear and bending interaction, especially in continuous beams and cantilevers where the maximum bending and shear happen in the same location. And that's when shear capacity can drop significantly. I said I wasn't going to talk about shear, and here I am talking about shear. We're not going to talk about web crushing either. But if shear is the quiet kid, web crushing is the poor kid that gets picked on by everyone. Alright, moving on, we're not going to talk about local buckling either, because you know that the section moment capacity, phi MSX, is equal to yield strength times the effective section modulus, and that the effective section modulus already accounts for local buckling. So as long as we keep the design bending moment below the phi MSX, local buckling won't be a problem. So yeah, local buckling is gone. And now we're left with one of the most important parts of steel beam design, which is lateral torsional buckling, also known as flexural torsional buckling. Structural engineers are familiar with this term, but if you say it out loud to non-engineers, they might just panic. And that's why from now on, we're keeping it simple. We're just gonna call it LTB. LTB is a failure mode where a beam moves sideways and twists at the same time. Not a great combination. And here's why. When a beam bends, part of it is in compression and part is in tension. The compressed part wants to buckle, while the tension part tries to hold things together. And that's why structural engineers add restraints along the beam's length to keep everything braced and stable. A classic example of this is a portal frame rafter with purlins and fly braces. Purlins restrain the compression flange for downward loads, and the fly braces restrain the bottom flange, which becomes the compression flange for upward loads. But of course, always follow the bending moment diagram. Since a portal frame has fixed connections, the bending moment change sign near the supports. That means for downward loads, the bottom flange near the supports is in compression, making it the critical flange. So you can tell that the critical flange changes along the beam, and it's a good idea to add restraints where it's required. And now, if you're wondering whether the inflection point, which is where the bending moment is 0, counts as a restraint, the answer is no, it doesn't. It doesn't, I'm telling you. Another great example we often discuss in our structural engineering community, that you can find a link in the description below, is how the nails and flooring help restrain floor joists, and how those floor joists then help restrain the floor beams. Each element helps stabilize the other, keeping the whole system in check. These restraints are considered effective if they prevent twisting of the cross-section and or lateral deflection of the critical flange. As a general rule, a restraint has sufficient stiffness if it can resist 2.5% of the force in the critical flange. Now you might be wondering, why the heck does the restraint needs to resist 2.5% of a force that doesn't even go into it? Well, my friend, I have no idea. Nah, just kidding. I'll never leave you hanging. The answer has nothing to do with strength. It's all about stiffness. A restraint needs to be stiff enough to shift the beam's buckling behavior into higher buckling modes. I'm gonna repeat that again because not even I understand what I'm saying. A restraint needs to be stiff enough to shift the beam's buckling behavior into higher buckling mode. Just like how adding a stiff restraint at mid-span of a compressed column forces it into a second mode buckling shape instead of the first. And it's the same principle. If you ever design a column, you will understand that. If you don't, just comment golden rules of steel column design and I'll make a video on that. Anyway, so a smart dude came up with this 2.5% rule as a practical measure to ensure the required stiffness. This guideline is found in clause 6.6.2 of AS 4100, but it doesn't provide an explanation for this specific percentage. You might need to do some digging or just trust the process. I believe I read somewhere that codes from the 1980s used to include stiffness calculations, but in more recent standards, such detailed explanations have been omitted. So while the exact origin of the 2.5% figure might not be clearly documented in current standards, it's a rule of thumb that's being adopted over time to ensure adequate restraint stiffness in steel structures. Alright, let's move on. The cross sections of a beam can be classified as full, partial, or laterally restrained or unrestrained. We head to our engineering second brain and then click on beams, steel beam design, and then designing a steel beam. If we scroll down, we have a section on restraints at cross sections, and full restraint, which is represented by the letter F, prevents the lateral movement of the critical flange and prevents or partially prevents twisting of the cross section. This image on this section denotes how you can achieve full restraint in a cross section. Now if we scroll down up to partial restraint, which is represented by the letter P, and partial restraint prevents lateral movement at a point in the cross section other than the critical flange and partially prevents twisting of the section. And you can tell by these images that the restraint or the secondary beam is connected to the non-critical flange. So here, for example, the secondary beam is connected to the top flange, but in this case, the critical flange is the bottom flange. So for this type of connection, you would achieve a partial restraint. After that, there's lateral restraint, represented by the letter F. And lateral restraint stops the lateral movement of the critical flange, but does not prevent the cross section from twisting. That's the typical case of a purlin connector to the rafter. As long as the top flange of the rafter is the critical flange, you will achieve lateral restraint. And finally, we have unrestrained cross sections, and that offers no restriction against lateral movement or twisting of the cross section. So it doesn't comply with F, P, or L. Now let's clear up a common misunderstanding. Full lateral restraint means the entire segment of the beam is prevented from lateral buckling. So you can use the full section moment capacity phi MSX. A fully restrained cross section means only a specific point on the beam is restrained, but the beam can still buckle between those restraints. So the term full lateral restraint should not be confused with a fully restrained cross section. I hope that makes sense. Designing a beam for lateral torsional buckling is actually pretty simple. In theory, if you look at the code, you will find an equation that looks something like this. Alpha S times alpha M times the section capacity. Since we already know the section capacity phi MSX from the tables, all we need now are the two mystery variables, alpha M and alpha S. Seems easy, right? Well, not really, because that nice clean formula actually looks more like this. Of course, we're not gonna sit here crunching numbers. Instead, we can just use a spreadsheet, software, or simply look up the values in a table like this. But here's the thing, even if software or tables do the math for you, you still need to input the right design parameters and interpret the results correctly based on design codes. And even if you go all out and build a fully detailed FEM, which, let's be honest, is not practical at all, you still need to understand what I'm about to show you. So let's break it down. Lateral torsional buckling can seriously weaken a beam. Take a look at this chart for a 410 UB 53.7. The bending capacity drops from 304 kN when fully restrained down to just 33 kN for a 16 meters long unrestrained segment. That's a massive reduction in capacity. What does this mean in real life? If we had to design a 16 meters unrestrained beam to carry a 304 kN bending moment, we could not use the 410 UB. We would need a 310 UC 158 instead. And guess what? That 310 UC 158 is 100 kilos per meter heavier than the UB. Over 16 meters, that adds up to 1.6 tons, which is almost 2 small cars worth of extra steel. This is exactly why structural engineers always find ways to laterally restrain beams, because the alternative is way too heavy and expensive. So let's see how you can do that. Imagine a 12 meters long steel beam with a point load at mid-span. We are classifying the ends of this beam as partially restrained because we are assuming we have a connection similar to these images on the right hand side, which means that that connection is restraining the non-critical flange of the beam. Because if it was restraining the critical flange, we could classify those ends as fully restrained. And then at mid-span, we are classifying the cross-section as fully restrained, which is represented by the letter F. And that is because we are assuming that this point load of 50 kilonewtons is coming from a secondary beam, which is connected to the top flange of our main beam. And we know that the top flange of this beam is the critical flange, because we have a point load, and that point load is going to push the beam downwards, and then we're going to have compression at the top flange and tension at the bottom flange. So step number 1 is to find the bending moment diagram. For a point load at mid-span, the design bending moment is PL on 4, so that means 50 kilonewtons times 12 meters divided by 4, that's equal 150 kilonewton meter. And we are dividing this beam in 2 segments. The first segment is PF, 6 meters, and the second segment is FB of 6 meters. So let's jump to step number 2, which is to choose a beam section with phi MB around M star for the unrestrained length. In other words, we're going to choose a section which has phi MB for 6 meters, close to 150. So let's say the range could vary from 100 to 160 kilonewton meter. So that means we could possibly choose a 360 UB 56.7, or maybe a 410 UB 53.7, or the 59.7, or also a 460 UB 67.1. I'm gonna choose the 410 UB 53.7, which phi MB is equal 108 kilonewton meter. I don't know if that section will work, it's just a trial for now. Now jumping to step number 3, we're going to find the effective length. The effective length is equal to KT times KL times KR times L. Let's start with the twist restraint factor KT, which we can find on table 5.6.3.A of AS4100. The restraint arrangement is FP, as you can see on our beam segments. So it's FP, FP. So that means the factor KT is equal to this formula. Don't panic, because super easy. We can just use this table on the right hand side. So this table on the right hand side gives us values of the letter A, and the letter A is equal to this portion of the equation. Therefore, if we come down here to 410 UB 53.7, we know that the letter A equals 140 millimeters. So letter A, 140 millimeters. NW is the number of webs. So if it's a UB, we have 2 flanges and 1 web. So NW is equal to 1. Now plugging the numbers into this formula, KT is equal to 1 plus the letter A, which is this portion of the formula, 140, divided by L. That's the length of the segment. So divided by 6 meters. That works out to be 1.023. So KT is equal 1.023. Next step is to find the load height factor KL, which we can find on table 5.6.3b of AS4100. And from this table, you can tell that if the load is positioned on the top flange, KL could be equal to 1.4, 2, 1, or 2, which is always greater than if the load is positioned at the shear center. And the reason behind that is that if you have a load applied to the top flange and your section starts deflecting and twisting, that load to the top flange is actually accentuating the movement of the beam. So that's why for the most cases, if the load is applied at the top flange, the KL will be greater than 1. And we know that our load is at the segment end because our load is applied at the end of the segment. Our point load is applied where the fully restrained cross section is. For that to be within segment, we would have to have loads applied within the segment. So let's say we had a couple of joists running here, some uniformly distributed load within the segment. That means we would have to use this portion of the table. And lastly, we're going to find KR, which is the lateral rotation restraint factor. Most of the time, KR equals 1, unless you have enough stiffness in the connection, or if you have a moment connection, then you could use a value which is less than 1. So finally, our effective length equals KT times KL times KR times L. So that is 1.023 times 1 times 1 times 6, 6.14 meters. Step number 4 is to find alpha M, which is the moment modification factor. Before we find alpha M, I just want to give you an explanation about this main table. So this table is based on alpha M equals 1, which is the most conservative value you can get for a beam restrained at both ends. So if we scroll down back to our table, so this is a uniform bending moment distribution along the beam, and alpha M equals 1. So 1 is the most conservative value you can get. Any other value that you can get from this table will be greater than 1. And since phi MB is equal to alpha S times alpha M times phi MSX, that means the greater alpha M, the greater our capacity. So if we use only 1, it means we're being very conservative. If we use for example 1.75, we're increasing our capacity 75%. You could possibly finish the calculations here. We have the effective length, which is 6.14. So you could come back to this table and then find the value in between 6 and 7, which is 6.14. You could interpolate those numbers and find a value that is greater than 150 kilonewton meter. Right? So you could come back here and probably just choose a 460 UB 67.1, and that gives us 161 kilonewton meter. So let's say for a 6 meters unrestrained length. So I would say that, for 6.14 meters unrestrained length, that should be alright. I could finish my calculations here and move on. Or if you want to optimize your design, you can find alpha M. And then when you find alpha M, you're going to multiply by the numbers on this table. And that's exactly what we're going to do right now. So if we scroll down back to our alpha M table, you're going to find the image that represents the point load, which is this one. The point load is at the mid-span. That means A equals 0. Therefore, the moment modification factor alpha m equals 1.35 plus 0.4 times 2 times 0 divided by L squared. So that means this part of the equation is 0, and we've got left 1.35. We also have some tabulated factors for the bending moment shape, for the distribution of the bending moment. So that looks like our case, which is a point load, and we've got 1.35. If you have a simply supported beam with a uniformly distributed load, you could possibly use 1.13. What this table is actually telling us is that if we have a uniform bending moment distribution, that means our compression flange is working hard along the whole length of the beam. And in this case, alpha m is equal 1, which is the worst case scenario. Now in our case, since we have a point load, that means our bending moment shape is like this. So this area is not being fully utilized. The compression flange, it's not working as hard as it is at the mid-span. Let's imagine we had a uniformly distributed load. The bending moment shape would be something like this. And then you can tell that compression flange is working a little bit harder closer to the supports, a little bit harder than for a point load. We still have this area here to be utilized, but at the same time is working harder than if we had only a point load. And that's why for a uniformly distributed load you have 1.13. So the last step is to multiply alpha m by phi mb. So we chose 410 UB 53.7, which phi mb is 108. 1.35 times 108 equals 145.8 kilonewton meter, which is less than 150. Therefore, that's not okay. Remember, if we go back, our design bending moment is 150 kilonewton meter. So we need something greater than that. So if that beam didn't work, I'm just going to go one size up. So that's a 410 UB 59.7. And that is a 129 kilonewton meter. So 1.35 times 129 equals 174.15, which is greater than 150 kilonewton meter. Therefore, okay. And then lastly, we've got a note here saying that in reality, we should interpolate the table to find phi mb for an effective length of 6.14 meters, right? Because our effective length is actually in between 6 and 7, is 6.14. So in reality, we don't have 129 kilonewton meter bending capacity. We have a little less than that. You can interpolate and find the real value, or you can be very conservative and choose 7 meters. But in this case, this section wouldn't work. You would have to choose one section above that. But I'm just assuming that 6.14 meters is very close to 6. And we also have some extra capacity from 175.15 if compared to 150. So that's 24.15 kilonewton meter extra capacity. Therefore, I'm just assuming that section is okay. And that's how you design a steel beam against lateral torsional buckling. Just a couple of final comments. Beams that are relatively strong at resisting torsion compared to their bending resistance are generally not susceptible to torsional buckling. So square and circular tubular hollow sections will have the member moment capacity equals to the phi msx, the section moment capacity. However, rectangular hollow sections can be
susceptible.
However, rectangular hollow sections can be subject to lateral torsional buckling for bending about their major axis. If the bending is about their minor axis, there is no lateral torsional buckling and the bending capacity is phi msy. Not phi msx, phi msy. This is the case of a wind beam, Whenever I have to specify a wind beam, I try to use tubular section. If it is an RHS, the wind load is causing bending about the minor axis, and you can use phi MSY. Same for open sections. If the bending is about y-axis, LTB will not happen. Alright, thanks for watching, and I'll see you in the next video.